All right. Hello, everyone. Welcome to today's session. Um, what we will do is first we will go through uh, doubts. If you have any doubts, you can ask me. If not, we will move forward with today's agenda. So you can ask me doubts if you have any doubts in lectures or previous uh, uh, discussions. Don't have any doubts? All right. Um, I hope there are no doubts. So maybe I will go forward with today's agenda. If you have any doubts in between, you can stop me anytime and you can ask me. Okay. So what we are going to do today is uh, we are we are going to do some solutions to Navier-Stokes equation, which is week 5 content, I guess. So week 6 is actually turbulence, right? Um, if you so I've gone through the assignments of turbulence, and I'm sure that the questions are pretty straightforward. So if you have gone through the lectures, you would be able to answer those questions. There were no um, problem questions like problem solving questions in turbulence. So that's why I thought maybe I will teach you something else different, which is more interesting. Still, if you have any doubts in week 6 content, still you can ask me. Um, if not, we will go ahead with today's quasi-Richo method. So, Nidharan, do you have any doubts?
Yeah, yeah, actually, I have a doubt in some questions in week 5.
Okay,
Uh,
we can go through that before. Sure. So, what are
questions,
those questions?
question number 5, 7, and 8.
All right. So, week 5 quiz, right?
Question 5, 7, 8.
Question 5, 7, and 8.
Yeah.
Okay. All right. So, question 5 is for collocated grids. Pressure is stored at dash and velocities are stored at dash, right? So, um, can you recall what is collocated grid?
Actually, we used to point the variables at same point.
Right. So usually in these grids, actually we will implement these grids only in finite volume method, right? So usually in finite volume method, let's say if you have a mesh and grid both are same. So let's say you have a mesh like this, okay? So in a finite volume method, what we will do is we will store everything at cell centers, right? uh, that is uh, that is clear, right? So finite volume method is actually for a small control volume, right? So if it is for a small control volume, we will store the variables at the cell centers, okay? So when it comes to collocated grids, what happens is we have few variables like velocity u, v, and p, right? So we can store all these variables at the same place at the cell center, or you can store it at the cell faces if you want. So that's when these the two kinds of grids is being classified. Okay, so one is collocated grid, one is staggered grid, right? So in collocated grid, what it actually means is, let's say x is velocity, okay? Let's say x is velocity, u and v, and circle is pressure. So in collocated mesh, what we will do is we will store everything at the cell centers. Okay, so that is the definition of collocated grids. Okay, so as per the question, what they were asking is, for a collocated grid, where do you store pressure and velocity? So both pressure and velocity we will store at cell center. But in staggered grid, what we will do is, so we have a mesh same as before, right? But what we will do is, um, we will store the uh, pressures at the cell center. Okay, so okay, sorry. So pressures are circle, right? So pressures at the cell center, we will store pressures at cell center, and we will store velocities at the cell faces. Okay, so that is the difference between collocated and staggered. This is staggered. And do you know why we are doing this?
No, no.
Okay, so what we usually encounter is, when we deal with collocated grids, um, uh, it is easy to implement, because you no need to have any separate variables, like in same cell center. Let's say you have 10 cells, your u, v, and p is going to be 10, right? You will have 10 datas. But in case of cells, you are going to have different numbers. It can be 11, 11, and it can be 10. So those incompatibility will be there if it is a stagger. If it is a collocated, it is going to be simple, and it is also easy to implement. So when you try to implement a algorithm, to solve an Navier-Stokes equation using collocated grid, it is far simpler than the staggered grid. But still we go for staggered grid, because this pressure velocity split will happen. So what happens if you have a um, uh, so we have a pressure gradient term, right? So what we do is, we will multiply velocity to the momentum, or we will take the divergence of momentum equation, and we will substitute it in the continuity, and we will end up with getting some pressure Poisson equation. And in the pressure Poisson equation, uh, uh, when we discretize it, we will end up having pressure velocity split. So what it means is, let's say if you have a grid like this, and let's say here the pressure is 50, okay, and here again the pressure is 50, and in between there is 100 and 100, okay. So this pressure velocity split, what happens is, when you find the gradient, you are interested in pressure gradients, right? When you find the gradient, if this is I comma j, this is I minus 1 comma j, this is I plus 1 comma j, this is I minus 2 comma j, I plus 2 comma j. So what happens when you store it in the cell center, when you try to predict the pressure gradient, so actually it becomes like p I plus 2 comma j minus 2 p I comma j. So it comes through derivation. So maybe you need to uh, go back to the lectures and check how this derivation comes. Okay, so it becomes like this. So what happens, actually there is a pressure gradient from 50 to 100, there is a pressure gradient, right? So 50 by delta x is there. Similarly from here to here, there is a pressure gradient 50 by delta x, right? But uh, when you develop the algorithm for the collocated mesh, you will end up some you will end up in relation something like this. So this tells that it's, let's say, I is 50, so minus 2 times 50 plus 50, right? So this becomes 0, like it tells that there is no pressure gradient. So this is called pressure velocity split. maybe we will look into that in today's quasi-Richo method also. So, uh, so that's what I will derive it. So if you don't understand right now, it's fine, but I will derive it how it become how the pressure velocity split happens. Okay, so right now you keep in mind that collocated grids end up in pressure velocity split, but there are some algorithms which takes care of this also. Okay, so but in staggered grid there is no chance that there will be a pressure velocity split. Okay, so that's why we store the velocities at the cell faces.
Okay, okay. In collocated case, we may either store values at cell center or at cell face, right?
No, in collocated grids we will only store it in the cell centers.
Not in cell face,
No, we don't store it in the cell faces.
but in lecture I saw like that. That is why I'm asking. Actually, the professor in slide pointed that one pressure, one velocity in one direction. At phases, he made it. So, that's why I'm
So
asking.
uh, yeah, maybe we can go through the lectures again. But as far as I remember, what we do is we store the variables at the cell center. We don't store variables at the cell faces. It's basically because you know it's a finite volume method, and finite volume method is constructed over a control volume, and within that control volume the variables doesn't vary. Okay, so I think I have mentioned this before, right? So within that control volume we have only one data. Okay, so if this is the control volume, so uh, I'm not sure where I mentioned it, but anyway, so let's say this is the control volume we have. Okay, so in a finite volume method, what we say is we will store the variables at the center. Let's say velocity v. Okay, so this v is actually averaged quantity within that control volume. There is no distribution of velocity. There is no function of velocity within that control volume. We have only one data, velocity data, uh, uh, in that control volume. So that's why we store variables only at the control volume. We don't, I mean, cell centers. That's why we don't store it in the phases. Actually, the control volume is constructed along around the cell center. Okay.
Okay, let me recheck the video. Lectures.
Yeah, yeah. We can
Let's. Okay. Let
we
us
can
move.
go through the videos once again.
Yeah, yeah.
Uh,
Okay.
if you if they still say like that, what you can do is you can refer to few books like Vestig and Malasekara. You
Uh,
can refer to that book. Maybe it might be fault in their presentation, or I will also look into that. You don't worry about that.
okay,
But
okay.
as far as I remember, it is just cell center. We just store it in the cell center.
Okay, fine. Then regarding seventh question, actually I couldn't understand the nature of question. Which property calculation staggered grid should be avoided means what is it? I couldn't understand that.
So it is asked which property calculation staggered grid should be avoided, right? Um, so so let's understand why staggered grid we need to use, right? So one thing I told is there is going to be a pressure velocity split if you don't use staggered grid, and that's because uh, based on the pressure gradient between the cells, there's going to be flow, right?
Actually, in if you use collocated grid means it doesn't tell us the pressure gradient, right? It actually in your problem you mentioned the 50, 100, 50, 100, 150 like that you mentioned now.
Mm-hmm.
In that case, there is pressure gradient, but due to the formula you have written on right side, the pressure gradient is supposed to be zero.
Right.
So that is the a nonsense,
Yeah.
right happening.
Right.
So that is a problem with collocated, right?
Right,
So that is when we are moving with staggered grid.
right. That's why we use staggered grid.
Okay. Okay, now you continue. Staggered grid.
So now, so it is actually for pressure and velocity. It is so the answer is you should avoid it for pressure and temperature. That's because pressure and temperature are two properties which is not related to each other, right? So the pressure distribution is not going to affect the temperature, or the temperature distribution is not going to affect the temperature. I mean the pressure. The basically in this case it is not going to affect, right? For a uh, like for an incompressible flow, right?
So,
There is no need for you to store temperature at the cell faces and pressure at the cell centers.
okay, then actually, why I should avoid that? Why I should
So
avoid that property?
so um, see the temperature, um, it's not a convective quantity. It's so pressure and velocity are coupled. Pressure and temperature are not coupled, right? So um, if you store these things, if you store temperature at the face and pressure at the center, so it indirectly gets coupled, which doesn't make sense, right? So why pressure should affect the temperature, or why temperature should affect the pressure? So the formulation should be consistent.
Actually, what kind of fluid flow we are dealing with currently? Incompressible flow, right?
Right, incompressible flow.
So, actually, pressure and temperature are related only, right?
So okay, so in an incompressible flow, you no need to solve for energy, right? Why you want to solve for energy? So if you let me write the equations. So you have a continuity equation and you have a momentum equation where density is constant, right? So because it's an incompressible flow, there's going to be dou u I by dou t plus there's going to be a convection and there's going to be a diffusion and there's going to be a pressure gradient, right? Now, this pressure is not related to density. Density is going to be constant in our incompressible flow. So, these two equations are fully decoupled with the energy equation. So, let's say there is an energy equation. Okay, let's write it as a enthalpy equation. Okay. Similarly, there will be a convection term for enthalpy, right? And there will be this del square T term. Um, so these things, right, plus some more terms will be there, some q addition, those terms will be there. So uh, there is no link between these two equations. Like this is a continuity and momentum, and this is energy equation. So energy equation is where temperature comes, right? So you no need to find temperature to find any of the quantities. So in this case, you need to find u, v and pressure. Okay. So this u, v and pressure doesn't depend on temperature.
Okay, okay.
So you no need to calculate energy at all. You no need to calculate temperature at all. In case if you want to calculate, uh, so if you see, temperature is dependent on U, V and P. Okay, not P but U and V, because there is a convection term here, right? But uh, U, V are not dependent on temperature. Okay, so since there is a convection in the energy term, you can solve continuity and momentum, and you can get velocity fields, and based on velocity fields you can separately solve energy. This doesn't come into the coupled manner. Okay, so if you see a simple algorithm, what happens is you will predict the velocity, predict the pressure, and then correct the velocity. There is no place energy equation comes in because you no need to solve energy equation. If you want to solve an energy equation which has convection also in within it, you will use whatever you predicted, whatever you corrected velocity, you will use it to find the temperature. So to find the temperature, you need velocity, but you no need temperature to find the velocity. Okay. So
Okay.
velocity pressure is not related to temperature. Okay.
Okay. Okay.
So uh, pressure and velocity should be coupled. It shouldn't be splitted. Okay. But pressure and temperature, you no need to couple it. In fact, you should not couple it because it doesn't affect each other.
Okay, so temperature is independent of velocity and pressure. So velocity and pressure are independent of temperature, right?
Exactly.
If temperature doesn't affect the velocity and pressure, then why should I avoid it?
So if the temperature doesn't affect velocity and pressure, you should avoid it, right? So if you store temperatures and temperature at the faces, okay, um, what happens is this pressure will affect the temperature, right? Because pressure is in the cell center. Uh, because of calculations, it can affect the temperature.
Oh,
So
okay.
actually, your question is right.
Actually, and the
Right,
question
right,
itself, I am not satisfied with the question itself.
right. So okay, maybe I will look into it and come up with a better explanation. Okay,
Yeah.
in the
Okay.
next session, I will come up with a better explanation for it.
Yeah.
You can also go through the lectures once again, uh,
Okay.
but I will convince you in the next lecture. Sure.
Yeah. Okay. Thank you very much.
So the next one was eighth one, right?
Yeah, eighth one.
What was the problem with eighth one?
No, not a problem, but general understanding of that I require.
Okay, uh, so they were asked to match the following. If the flow is from right to left, and we are interested in evaluating the value at phase W, then value required at node is okay. Um, it is from right to left, right? So from east to present, present to west it goes, right?
Yeah, from east to
So
west.
if it is upwind, for pure upwind skin, you need to go from 5P to 5W. So for the first one, it would be just 5P, right? Is that clear?
Uh,
So,
no, actually in upwind we will take one extra turn in along the direction of flow.
right. So here the direction of flow is in this direction, from right to left, right? So present cell is here. Here we have west. Here we have east. So upwind means what happens? 5P is equal to 5W, right? That is how you do, right?
Okay, okay, okay.
So because property is moving from here to here. So from 5P you go to 5W. So that's why first one is 5P. Similarly, for central differencing, it doesn't matter because it doesn't take care of direction of flow. So it would be uh, this would be east and this would be west, right? So if you want to calculate phi small w, it would be 5p minus phi capital W divided by delta x, right? This is central differencing, isn't it?
Yeah.
Right. So here also it's phi W. So this is upwind, this is central, and the next is quick. So what quick does is it takes upwind also into consideration, right? So what it will do is phi w will be a function of it will have central differencing phi p phi w, and it will also have upwind thing. So upwind will be from east, right? Phi east. Is this clear?
Okay, right. Fine, fine, fine.
So because it takes upwind also into consideration in addition to central. So central needs phi p and phi w. For upwind, you need another in the upwind direction. So it comes from east.
Okay, okay. Thank you very much.
So okay. About the seventh one, I will come up with better explanation anyway.
Yeah, okay. Thank you very much.
So does anyone else have any more question? I think Uzair has one question, but I think he is not here. Anyway, let him join. Uh, we will continue with today's discussion. So, what we discussed so far was if, do you have any questions?
Yeah, sir. Actually, no, sir. I am yet to watch week six videos,
Okay,
and I couldn't also follow week five thoroughly.
okay,
I will have to rewatch that.
okay,
But I'm seeing what you are explaining. I think once I watch the videos again, I will understand.
okay.
Thank you, sir. Okay.
Okay. So you may not you no need to call me sir. You can call me Ganesh. No problem. Um, week five lectures. I think it's mostly a solution to Navier-Stokes equation. How you are so for last 4 weeks we were discussing of different schemes, the finite difference, finite volume, and how to discuss each and every terms in any equation, right? In week 5, I believe that it is for a full Navier-Stokes equation. So because in a flow problem, you are going to solve a Navier-Stokes equation. For the Navier-Stokes equation, how are you going to take care of those nonlinearities? How are you going to go through uh, the flow chart, or I mean um, the structure of solution is what we discussed. So there are actually two types of grids: collocated grid and staggered grid. So what has been thought is actually collocated grid leads to pressure velocity split, and staggered grid doesn't lead to that. Uh, but today what I will do is there is one method called quasi-Richo method, and the extension Richo method is also there. So what they use is they will use uh, uh, they will use collocated grid. They don't they without use of staggered grid. We will be able to overcome this pressure velocity split. So we will quickly go through what this method does. Okay, so basically it starts from momentum equation. So first our cell control volume would be like this. This would be the present cell. Um, and it has east, west, north and south faces, and um, so basically we have three equations, like two momentum and one continuity equation. So first let's start with continuity equation. So for a finite volume method, you need to solve for uh, integral form of equations. That we all know. So for a continuity equation, what we have is v dot n dA is equal to 0. That's the simple continuity equation in an incompressible flow. So v dot n times dA equal to 0. This is a control surface integral. So what you can write is summation over all faces, right? Summation of over all faces u dot a AFRSF, so area of the face. This is how you will write, right? So if we do that, we see that there is a flux going out at east and flux coming in at west. So what you can write is u east times delta y times 1, because this area, the depth is actually I'm taking a unit width. Okay, so since it's 2D, depth is actually unit width. So if that is the case, um, uh, this is delta y and we have a unit width 1, right? So delta y into 1, and Similarly, this is east phase, the flux is going out, UE into delta y, and west phase flux is coming in, UW into delta y. So this is, since it is going out to positive, this is negative. So these things you know in a finite volume. I'm just refreshing. Similarly, we have for um, north and south, flux is going out and coming in. So what we are planning to do is we will convert this east, west, north and south in terms of I and j. Okay, so present cell would be I and j, east would be I plus half j, and west would be I minus half j, and south would be I comma j minus half, and north would be I comma j plus half. Okay, a standard notation. So if we try to if we try to change this uw in terms of I and j's, we will end up getting this star equation. So this star equation is actually the continuity, discretized continuity equation, and you see I have discretized it implicitly, right? Because i'm I'm taking the values at the n plus 1 time step, which is the present time step. Okay, so this is how you discretize a continuity equation in a finite volume formulation. Similarly, we have x momentum equation. Um, in x momentum,
Mr. Ganesh?
ha ha, Nidavan.
Yeah, actually, why we need to include that n plus one term above the u velocity? What is the significance of that?
So what we do is uh, one second. So Uzair, actually we will do this for next 20 minutes, and at the end of this session I will tell you about von Neumann stability analysis. Is that fine?
Okay, sir.
Okay. So coming to Nidaran's doubt, what happens here is uh, we have to, so this is a incompressible equations, right? So we have to uh, we are solving for unsteady incompressible equations. So we have velocities for every time steps, and every time step the velocity should satisfy the continuity equation, right? So that's why we took n plus 1 time step. Every time step we are going to have a so initially we will start with an initial condition, which will of course satisfy continuity equation. So our aim is to, for every next time step we compute, it should satisfy the continuity equation. That's why we wrote everything as n plus 1.
Okay,
Okay,
actually, irrespective of time, this continuity equation satisfies now. This,
right.
we
But
are getting.
we have
Okay.
velocities for every time steps, right?
Okay.
So if we have velocity field for every time step, my continuity equation should be satisfied.
Yeah, like basically we are dealing with steady or unsteady flow here.
Unsteady flow here.
Okay. Then in continuity, we should also include another increase in time that equation and additional time will come now in continuity.
So the equation would be something like this, right? Dou x of rho u equal to 0, right? This would be the equation.
Yeah, yeah, yeah.
Uh, Density doesn't vary. So what happens? It would be dou u by dou x equal to 0, right?
Okay, okay.
The unsteady part is not there in continuity equation, right? For an
Hmm.
incompressible flow. This is for incompressible flow, right? In compressible flow, density varies, so this whole term will be there.
Okay, okay, okay. Fine, fine, fine. Okay.
But the
Uh,
problem is unsteady. The problem is unsteady. Continuity equation uh, came out to be looks like steady, okay? Which means that at every time step, continuity is satisfied.
okay, okay. To put the importance of time here, we are including the n plus one.
Exactly. So
Yeah.
for every time step, whatever velocity you predict should satisfy continuity equation, because
Okay.
that's the basic conservation of mass, right?
Okay. Here n plus one signifies the present time or future time.
Present time step. So n is previous time step. Maybe I will write it down here. So n is previous time step. N plus 1 is present time step.
whether this is the same approach followed in books.
I hope so. Actually, I was taught like this. I'm not sure how it is followed in books, but this is how the notations are almost same. Okay,
Okay, okay, fine.
they might be like n minus one and n. They might have something like that, but most of the books follow n and n plus one.
Okay, okay, fine.
Easier way to use it. Actually. Okay, so
Okay.
that's why at every time step we need to satisfy continuity. That's why we need to have we have this star equation at n plus 1 time step. Similarly, we have x momentum equation where we have a uh, unsteady part, a convection term, and a diffusion term, and a pressure gradient term. Right? Since it's of a control volume, we have to integrate it over a control volume. Right? So because finite volume approach will use um, integral form of equations. So whatever the differential form of equation you have, you will convert into a integral form of equation. How do you convert this? You will integrate the whole equation over a control volume. Okay.
Yeah.
So now we have this equation dou by dou t of this convection, diffusion, and the pressure gradient term. So now you can simply discretize it like this, right? So it's a simple uh, Euler Euler explicit form. Here dou by dou t you can write it at u n plus 1 minus u1 divided by delta t, a simple uh, difference form. And then we have delta x and delta y because it is multiplied by control volume. So our volume would be delta x delta y into 1. So that one is it's a unity, so we just drop it out. So delta x delta y, and we are going to have convection and diffusion term, which we already know how to discretize using finite term. So I didn't write it for simplification. So you will write the same discretized form here. Okay, and we also have pressure gradient term. So here the pressure gradient would be dou p by dou x ij times delta x delta y into 1. Okay, because it is for a control volume. Okay, similarly you can write this for y momentum equation also. So this would be another equation. So now for any problem we need to solve this equation momentum, these two momentum equation, and then we need to solve this continuity equation. So if we look at this thing, we know velocities at n and pressures at n, which means at previous time step, but we don't know velocities and pressures at the n plus 1 time step, right? So if we have unknowns at both sides of the equation, we won't be able to solve it. That's why we will go for this prediction and correction um, methods, right? So what we will do now is we will try to predict the velocity. So in a quasi-Richo method, what they will do is we will they will predict the velocity without the pressure gradient. So we have this equation 1, right? We will rewrite equation 1 as rewrite equation 1 without pressure gradient, and the predicted velocity may not it usually will not satisfy continuity because we didn't account for pressure gradient, right? So let's rewrite this. So let's say the predicted velocities are u cap and v cap. What happens? U cap I comma j minus u at n I comma j divided by delta t times delta x delta y, and then we will have a convection term, and then we will have diffusion term. Okay, and we are going to we will be evaluating convection and diffusion at the nth time step to avoid complexities, because convection term is a non-linear term, and it's if you evaluate at the nth time step, everything would be known, so you won't end up having complexities. Okay, so in quasi-Richo method, we will treat this as explicitly, which means we are evaluating at nth time step. So if we look at this, we just removed this pressure gradient, and we replace this n plus 1 to be a predicted velocity. Now this equation can be solved, right? So this equation can be solved to get the predicted velocities. Similarly, you can write for um, v cap, right? So let me write that also. So it will be v cap I comma j minus v at n I comma j divided by delta t times delta x delta y is equal to minus convection y and diffusion y. Okay, so we will so this is the first step. Actually, this step is there in simple algorithm also. If you have gone through the lectures, you may know this. But here we are dealing with collocated mesh. We are not worrying about staggered mesh. So um, here we have. So now um, we have predicted velocities, right? U cap and V cap everywhere in your domain, because you can easily find it, right? You can take all the other variables to the other side, and you can find U cap and V cap. You no need to solve anything. So with these two equations, you can find U cap and V cap, the predicted velocity. Now the predicted velocity, of course, it won't satisfy the continuity equation, right? That is the problem. Now we need to correct the velocity. How will you correct the velocity? We ignore the pressure gradient. We need to somehow find the pressure gradient, and we need to use that pressure gradient to correct the velocity, right? So our step 2 would be to find the pressure gradient. Step 2 would be to find the pressure gradient or the pressure field. Okay, so how are we going to find this? So what we can do is, let's write this equation as equation number 2. Okay, so now we have equation number 1 and equation number 2, right? So what we will do is we will subtract 1 minus 2. Okay, 1 minus 2. Now what happens if you compare these two? um, so this convection term, diffusion term would be going, right? These two would be going, only pressure gradient term remains, and on the left hand side we will have uin, and uin will go away, right? Because we are subtracting these two, so we will end up getting rho times u I comma j n plus 1 minus u cap I comma j divided by delta t equal to minus dou p by dou x at I comma j at n plus 1 delta x delta y. Here also there will be delta x delta y, right? So what happens here is, now we can cancel this delta x delta x delta y here. So we can rewrite this equation as u I comma j at n plus 1 is equal to u cap of I comma j uh, minus delta t by rho times dou p by dou x. We haven't discretized this pressure gradient, we just kept it like that. We will see why. Okay, so similarly we can write Vinj, right? So it will be same as the above, but it would be dou p by dou y at I and j at n plus 1. Okay, so if we know the pressure gradient now, we can use this equation to find the corrected velocity. This ui n plus 1 and vi n plus 1 is the corrected velocity. Now our aim is to find this dou p by dou x. So what we will do is we will try to uh, we need to make use of, so what we use till now is a momentum equation. Now we need to make use of this continuity equation. So for this continuity equation, what we need is ui plus half j, ui minus half j, v I comma j plus half, v I comma j minus half, right? So let's try to write what is u I plus half comma j at n plus 1 would be. So how can we write this? So there is this control volume. This is I comma j. This is I plus half comma j, right? And there is another control volume. Maybe I will write it a little bit bigger. So would you guys like to guess? So this is I plus half comma j. This is I comma j. This is I plus 1 comma j. Okay, I need a velocity at I plus half comma j. How can I write the part? So you need you so as we said before, this is a collocated grid. If it is a staggered grid, we know the velocities already because we stored velocities at the faces. Here we stored it in the cell centers. So I have velocity at I comma j. I have velocity at I plus 1 comma j, and I need I velocity at I plus half comma j. So how can I do it? Can I write like this? I can write like this, right? This is called linear interpolation, right? Does this make sense?
Yes.
So, so this is where the pressure velocity split starts happening. Okay. So when you do this linear interpolation, you it as u I comma j, and when you do this interpolation u I comma j and u I plus 1 comma j, and let's say how will you do this? So we know that what we know is half into u I comma j would be u cap of I comma j. We know u caps, right? U cap of I comma j minus delta t by rho. We have this dou p by dou x I comma j at n plus 1 plus u of I plus 1 comma j cap minus delta t by rho dou p by dou x at I comma j n plus 1, right? So let's write it like this: half into u cap of I comma j plus u cap of I plus 1 comma j plus uh, minus delta t by 2 rho, and we have dou p by dou x at I comma j. How can we write? We can write it like p of uh, I comma j can be written as I plus 1 minus p of I minus 1 divided by 2 delta x, right? These are evaluated at n plus 1, a central differential, right? So similarly,
Hello?
this,
Yeah, actually, delta t by 2 rho, how you made that? Delta t by 2 rho.
so there is this half, right? We have this half.
Oh, okay, you have made the debate.
Uh,
Then, regarding the linear interpolation, how can we know that velocity is varying linearly?
velocity is not varying linearly. That is the approximation we are making, right? Linear interpolation. So this is a kind of approximation, right? Linear interpolation.
So we are
We
making.
assume that it varies linearly within the two cells.
Okay.
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 So when we do this, similarly we will have another. Sorry. So similarly we will have the other one, which is this would be I plus 1 comma j, right? So if we write I plus 1 comma j, it would be pi at n plus 1 and I plus 2 minus p I comma j at n plus 1 divided by 2 times delta x, right? So this is for u of I plus half comma j at n plus 1. Okay. Similarly, this is one equation. Similarly, you write u of I minus half comma j at n plus 1. Okay. Here what happens? Similarly, you will have some term minus delta t by 2 rho, and similarly you will have another term, and I request you to do this by yourself. So if you, and finally what we have is u of I plus 1 at n plus 1 minus u I minus half comma j at n plus 1 times delta x, right? This is one of the term in the continuity equation, right? If you look at here, we have this term, so times delta y, sorry. So if you do this times delta y, if you do this, you will end up getting some u caps and v caps, not v caps of course, u caps, I plus 1 or I minus 1, some functions you will get half times, and then you will also get delta t by 2 rho, and here you will end up getting the I plus 1 and I minus 1 gets cancelled, and you will end up getting p I ij and p I plus 1j, uh, could be like this. Okay. So divided by uh, delta 2 delta x. So this this is called pressure velocity split. So we will end up getting pi minus 2 comma j, and 2 times pi plus 2 I minus 2 and pi. We won't so this would be the function of pi plus 2 I minus 2 and then pi. Okay. So I will also upload the detailed derivation also. So I'm just giving you the gist. So what happens is it is not a function of uh, so this is not a function of I plus 1 and I minus 1, which doesn't make sense, right? Because from this control volume needs to, this control volume, the flow is coming to the control volume of I comma j, which means there is a pressure gradient from I plus 1 to I, right? So if you are not taking that into account, then whatever the solution you predict would be wrong. That's why this pressure gradient is wrong. So what is the assumptions we made is we made it to be linear interpolation, which is which if we suddenly want something at the interface, we will just do average of these two, right? That's what we end up doing. That is our instinct. Instinct tells us to do linear interpolation, but this will end up pressure velocity split. So now we have to go through some other process, which would be which is the basis of quasi-Richo method. I will continue this in the next class, uh, and basically quasi-Richo is more simpler to implement than a simple method. That's why if we were able to do good in quasi-Richo method, if you can understand quasi-Richo method better, maybe we can at the in coming classes we can solve some small problems like lid-driven cavity flow, which is um, uh, like test cases for everything. Okay. For whatever the program you develop. um, so I will continue this and finish the quasi-Richo method within next class, and I will also discuss the problem statement for lid driven cavity or any other flow, and maybe we can solve it in the upcoming class using programming like MATLAB or something. Okay, because since it is easy to implement, I am showing this quasi resource. Similarly, you can extend this approach to simple method. In simple method, we already know what is the algorithm, right? So in that way, you can uh, implement simple also. So by with this, I will stop here. I have few questions at the message chat. Um, um, Rekha is asking, is Navier-Stokes equation valid in low Reynolds number flow, 10 to 50? So no, Navier-Stokes is actually more general equation. It is valid in any flows. It is for any flow problem. It is valid actually.
But sir, in some textbook it is written like that in vacuum. If the operating condition is in vacuum, there you cannot. There Navier-Stokes equation is not valid like that. It is written in some textbook.
Right. So vacuum is different than low Reynolds number flow. In vacuum, there is no flow at all, right? So if there is a vacuum, there is no air molecules inside. There is no gases inside. So there is
No,
no
no.
flow.
If you calculate Reynolds number in that pressures, it will come around 50 to 10 to 50 Reynolds number. Means it is in a laminar region only. Uh,
Right. So I will tell you when Navier-Stokes is not valid. Okay. So
okay.
Navier-Stokes is not valid if your continuum approximation breaks down. Okay. This is the only place where Navier-Stokes is not valid. So it has nothing to do with Reynolds number. In fact, Reynolds number is defined based on the continuum approximation. If continuum approximation is valid, then Navier-Stokes is valid. So what is continuum approximation is uh, within that control volume or with any small length scale, if your flow domain is in that length scale, and if the variables doesn't vary that much. Okay, so let's say you have a small box, and in that you have some 50 some 10-50 molecules. Okay, molecules of air. Okay, so in that box, if you divide this one part, you will end up getting only one molecule, right? But if you have another part, this is end up getting another one molecule. But if you divide the other part, you will end up getting 1.5 molecules, right? So uh, here the variables are not continuous. Like for example, let's say for density, let's say density. Here it's actually one molecule per that volume. Okay, for this row one. So if for row two, this is row two, this is row three. This is also one per volume. This row three is actually 1.5 per volume, which means that row is not continuous. So if you have a rarefied gas flow, like gas flow in space, okay, then you won't be able to, you cannot find a small play, like a very small microscopic level of box or control volume where you can say that rho is continuous. Okay, so if you can't do that, you cannot define Reynolds number itself. What is Reynolds number? Reynolds number is rho u what is Reynolds number?
dV rho by mu.
Right. So right, like this, RL, right? Any length scale.
Characteristics.
So here this density and viscosity are properties. If the properties doesn't vary, if the properties are not continuous, you can't define a Reynolds number as far as I remember. Okay, so if you can't define a Reynolds number, then of course Navier-Stokes equation is not valid because continuum approximation is not valid. So only thing is continuum approximation should be valid at the scale you are working on. Let's say you are working on nanotubes or nano scale. There you might end up having some 10 nanometers, and within that nanometer your density might vary very large. Okay, or maybe there will be very small number of molecules which will go here and there inside. There you can't apply Navier-Stokes equation, right? But if you are in a macroscopic level, and if you are, let's say, analyzing a flow through a tap water or through a tap, or so there you have a fluid is coming out and its density is not going to vary, right? Vary in the sense in a microscopic scale, not a macroscopic scale. So if you go to gas dynamics, density will vary, but it varies macroscopically. In microscopic level, the density, viscosity, the properties doesn't vary. The viscosity, thermal conductivity, density, those properties doesn't vary in a microscopic level. So if it is continuous, then only Navier-Stokes is valid. So if you are saying that there is a Reynolds number for this flow, Navier-Stokes is of course valid. So
Okay.
maybe if that book is telling you it is not valid, maybe you need to go through in what context they are telling. Okay.
Okay. Okay.
So
Whether at the end of this course you will get a hands-on experience on any CFD softwares apart from MATLAB?
So actually, the motive of this course is not to get uh, hands-on on softwares. So the motive is to understand CFD in a fundamental level, right? So so that you can apply this knowledge in any software you like, and you end up getting a proper solution. So we won't be teaching you softwares, but we'll be teaching you concepts which you can apply in your software, and you can end up getting a proper solution. Okay.
Okay.
So understanding concept is more important.
Yes.
Right? So coming back to Uzair's question, so could you please explain about von Neumann stability analysis? So I'm not sure how deep I should go, but why we need to do stability, you should be aware, right? So why we need to do stability analysis? Who's there? Are you there?
Yes, sir.
So why do we need to
Sir,
do stability? Hmm.
to need to check whether to need to check the stability of that of the system, and also the convergence is like the flow should be converged. So that's why according to that equivalence theory.
Right.
Right.
So in our case, what we have is let's say we have a continuity equation. Okay, dou u I by dou x I equal to 0, or let's say we have dou u by dou x, dou v by dou y, and dou w by dou z equal to 0. So what we usually do in discretization, we will try to approximate each and every derivative, right? Dou u by dou x is like we will have a grid like this, I plus 1, I minus 1, and what we will do, we u I plus 1 minus u I minus 1 divided by 2 times delta x, all these things we do, right? So we do discretization. Is that clear? Because we cannot solve a partial differential equation, right?
Yes, sir.
So what we will do is we have a partial derivative. We are trying to approximate it in this form, right? So what happens when you approximate in this form? Uh, if you go through the lectures back, or our discussion sessions back, uh, we have another some order of delta x, right? Some truncation terms are there, right? Number one. So there are some error terms which we ignore it, right, when we are doing this approximations. Another one, so in your computer, let's say 32-bit or 64-bit, uh, usually what we will do is we can't store the data for a very long, for more decimal points, right? So let's say velocity is um, 0.0054. What we do is we will approximate it as 0.005. So what we are doing here is round off, right? So for example, I showed you some four, so total five significant digits, but in computers it can go to 17, 18 digits, right? So in what we do is we have to do some round off, right? So this is these are round off errors, okay? And there are few more errors. So these truncation errors, round off errors, and a few more errors, what it can do is, based on our scheme. So whatever we did is CDS scheme, right? A central differencing scheme. Based on our scheme, these errors might grow, or it can decay, or it can be constant. Okay. So based on this scheme, these errors might grow or decay, or it can be constant. Okay. So what we need is, we don't want error to grow. We want solution as close as possible. That's why we do stability analysis. And there are different ways to do stability analysis. One is von Neumann stability analysis. So when we say stability analysis, we don't want error to grow, okay, from for each and every iteration. Is that clear?
Yes, sir.
So stability analysis is done is to understand whether error grows or decays, and there are different ways of doing it. One is von Neumann stability analysis, and what they do is they consider error term to be um, some Fourier distributions, right? Error can vary anywhere, right? So this is I, this is I plus 1, and this part is I minus 1, right? So error can be random, it can be any value. So this error they are going to define in terms of Fourier series, right? So they will define this error in terms of Fourier series, and they will analyze whether this um, error is going to grow or decay as we move forward in time, or as we go from one iteration to next iteration. Okay. So to have an in-depth knowledge on this, you please go through our previous discussions and even lectures. Okay. If you have any more specific doubts, you can ask, or you can come back and ask in next session too. Is that fine, Uzair?
Yes, sir.
So you understood, right, why we are doing stability analysis, and what is von Neumann stability analysis, like broad picture.
Yes, sir.
Okay. So you go through the lectures
Thank
once
you.
again, and let me know. Okay. If you find any difficulty in some part, you let me know. Huh? So does anyone else
Thank you.
have any more questions? We will complete this quasi-Richo in the next class, and we will try to uh, model the um, lid-driven cavity flow, or our first problem. What is the problem? The flow through a channel. Okay. Either of this we will